Hello, this is Dr. Coburn, and I'm going to talk to you about different types of spectroscopies because it's something that I have a lot of experience with. This kind of information is found in your Harris textbook in chapters 18 through 21. And you'll find a lot of this material in chapter 18. We're only going to cover a little bit of what was in chapter 19 about applications. We'll talk, and then a lot of chapter 20 on spectrophotometers, and then a lot of what's in chapter 21. Okay, but it won't necessarily be in the same order as those chapter books. Okay, so when you go into a laboratory, chemical laboratory these days, it doesn't necessarily look like these pictures, a bunch of chemicals, benches where you mix things. What you tend to find these days, this is a traditional chemistry lab, what you find instead is a bunch of instruments, a bunch of boxes. They're not black boxes anymore. They tend to be white, a bunch of white boxes. And these are different kinds of spectrometers. So a lot of modern chemistry labs, that's why we're showing you this, you're going to run into a lot of spectrometers that are used to make rapid measurements. So let's first talk about what is meant by spectroscopy, or you'll run into the term spectrophotometry. All right, spectroscopy and spectrophotometry. So spectroscopy, the interaction of radiation with matter, right? How does radiation interact with matter? What kind of things, what kind of absorptions, emissions, what kind of things can happen, all right? And that term spectroscopy isn't just radiation. Now it includes other kinds of interactions. You can send an ion in or something else, or an electron in and cause some change and then get some emission or something like that. But all these spectroscopies tend to have you measure some spectrum, which is some either a wavelength range or an energy range, as we'll show you some of these. Maybe it's a mass range. Maybe you're measuring the mass of the particles coming out, and so we call that a spectrum. All right, so these are generally spectroscopies, and you learn about the materials among other things, depending on how they interact with matter. Now, there's another term, spectrophotometry, which is a little more specific. In this case, it's got to be just light, right? But it's used to measure chemical concentrations. So this is using Beer's law, right? Depending on how much light is absorbed, normally, it's not always absorbed, but Beer's law is always absorbed. But depending on how big your signal is, that's how much material there is. So that's one kind of spectroscopy, which we'll call spectrophotometry. And sometimes you'll see it, the older term colorimetry, right? Again, and this generally refers to just visible light and how much light is absorbed at a different wavelengths, in the visible. All right. So why do we care so much about spectroscopy? All right. Well, it has quite a few advantages over other techniques. First of all, or traditional techniques. First of all, it can be very rapid, right? Instead of mixing a lot of things and trying to figure out what interacts with what and then weighing something out, you can just stick it into an instrument and very quickly get some interesting results, maybe quantitative results. It frequently doesn't need much sample, right? You don't have to actually weigh something out. You just have to get a small enough light source to go through a little container and see how much it interacts. It can be very accurate and reliable, all right? It can also be very selective and sensitive. And finally, it can be automated. So you can have some instrument, say, that's just watching a factory or watching something happen. Maybe you're doing an experiment where a column and stuff is coming out of the column, and rather than taking little samples and doing an experiment on each one, you just watch it with some light maybe going through it, and you can see when something is coming out, all right? So there's a lot of great advantages for it. What's the disadvantage? Well, I guess one of the big ones might be that it could be more expensive, right? So that's always a concern. And so sometimes you don't see it used because it's expensive to have a lot of these instruments. A wide array of these techniques, these spectroscopic techniques, are applied in virtually every kind of scientific research. Not just analytical chemistry. Analytical chemistry is just measuring normally how much of different things there are. So you'll find it in environmental analysis, right? Environmental chemists will look at it. Biomedical science uses it all the time. Forensics, police kind of work where they use it. Material science, even space exploration. How the heck do you think they figure out what the elements are that are in different planets' atmospheres, all right? They didn't go out and actually grab some of this, what's in those atmospheres. They looked at it spectroscopically, okay? And it's widely used also to figure out the molecular structure of a sample. So you've got a sample, an organic compound, you've purified it, you made something in the lab, and you want to figure out what it is. It's heavily used in that area. So it's a big field, all right? It's a big field, spectroscopy. So let's come up with a couple ways to break it down so we can get our head around it, right? This large field of spectroscopy. One way would be to classify it by the kind of species that you're looking at, right? So that could be atomic spectroscopy and molecular spectroscopy. And atomic can involve the absorption. Usually when you're absorbing light, the light is in the ground state for an atom, right? The atom, if you can get it into the gas phase, it'll be in its ground state. Okay. Whereas in molecular spectroscopy, it's more complicated because in addition to the electronic states, these are the 1s, the 2s, those things you learned about in your first semester of general chemistry. There's also rotational states and vibrational states, right? And that causes it to get much more complicated as soon as you have more than one atom. So as well as you have electronic states in molecules. So it gets much more jumbled up in molecular spectroscopy. Okay. And of course, atomic spectroscopy doesn't have to be a pure atom. It could be an atom that you have in a compound and you say put it into a flame, right? And everything falls apart in the flame, and you're looking at emissions. Right, so that gets used a lot too, and it's typically done with metals because metals have a lot of absorb light and emit light in useful wavelength ranges. It doesn't get used for things as much like carbon or nitrogen, hydrogen, things like that. And the molecular species you look at, they can be big molecules. We're not just talking little things. These big biomolecules. DNA, things like that, or anyway, proteins. They can be very large things that you're looking at with these spectroscopic techniques. All right, so that's one way to break down the field as to whether you're looking at atomic or molecular species. We can also try to break it down by the wavelength range that you're looking at. So by way of review, remember the electromagnetic spectrum is broken down into large ranges. And so the ones we're going to care about, let's look down here in this range here. This thing is showing wavelength at the top, all right? And the wavelength here, you can see it starts off in nanometers. Eventually you measure it in meters. That would be actually over here. And it can be even larger than meters, all right? But we break them down and we have names for them. So for instance, X-ray is down here. And then we have ultraviolet. And of course, the very important visible region, which is actually just a very small portion of the electromagnetic spectrum. Then comes infrared, right? And then microwave, and finally radio wave. All right, and we're going to talk about spectroscopy in almost all these bands, not gamma rays, but all these other bands are used for various forms of spectroscopy. So now these were the wavelengths, right? You can also talk about it in terms of frequency, recall. And they're related by this equation here, remember. Wavelength and frequency are related by the speed of light. And so these things can be done in hertz, right? In hertz. Okay. What kinds of wavelengths are used for what kind of spectroscopy? What do you learn about in different regions of the electromagnetic spectrum? So we're classifying by the type of radiation. So X-rays have the most energy, right? The energy of an X-ray is much more. These are in reduced energy. as you go from top to bottom here. So the wavelengths are very short. All right, they're a few nanometers to fractions of a nanometer, the wavelength. And that's enough energy that you can take an electron out of an inner shell of a large atom, and the K shell or the L shell, which is the 1s, 2s, or the 1 or the 2 principal quantum number, and put them up into a higher energy state, or for that matter, you can ionize, completely break bonds with these X-rays. All right, so that gets used, as well as X-rays are used to kick out the electrons, as well as it's used for in diffraction, so you can see the structure of crystalline materials using X-rays. All right, then you come down into the near ultraviolet and the visible range, and this is enough energy. This is so we're about 200 to 750 nanometers. This is enough energy where you're moving electrons in the valence state up to a higher energy level. So these are electronic transitions of the higher energy electrons, the valence band. So we're not talking about core levels anymore. There is enough energy to raise an electron from a core level only with valence electrons, which they could be in an atom or in a molecule, some of the higher energy states. Now when you get further down, now we're going to switch from nanometers because it's convenient to microns. So now you're in the micron range, wavelength range. That's the infrared. And there we're talking about molecular vibrations, right? So you're not actually sending electrons into higher electronic states. You just have some vibrating species, like a vibrating spring. Think about, say, the OH bond in water, right? Because that OH bond, it can vibrate back and forth, and it turns out it has quantized states, quantum states, just like electronic states, but they're now vibrational states. And so you can change the vibrational state with infrared, with that kind of lower energy. If you get down even lower into the microwaves, then you're talking about, just the far infrared, you're talking about molecular rotations, right? The whole molecule rotating, or rotating about a bond, okay? That takes less energy between the states there. And finally, when you get down to even lower energies, now we're talking about meters, right? Those are radio waves, near AM, FM band, those kinds of radio waves. And that's not enough energy to cause a molecular or rotation vibration, but it can lead to the changing of the spin, which we haven't learned much about, but this is essentially the upspin and the downspin. Remember, the electrons can have spin. Remember atomic physics, or when you learned about the atomic structure, there was an up and a down spin. We didn't pay much attention because they are the same energy, whether an electron is spin up or spin down. Or this is actually the nucleus. The nucleus can have a spin up and a spin down if it's an odd mass nucleus. Right? So it turns out there's an up and a down spin, but they have to actually be in a magnetic field in order to have a different energy. So that's the kind of stuff that's done in radio waves. We'll talk a little bit about that later. Okay, spectrophotometry that we talked about to measure the quantitative amounts of materials. To do that, it's mostly the near UV, visible, or infrared. So we're going to be talking mostly about those ranges when we're talking about measuring the quantitative amounts of things. The X-rays and the microwaves, the radio waves, those are more to learn about the structure of a material. So you'd tend to apply that when you had a pure material. All right, you take a material and you've isolated it, maybe in organic chemistry, so you only have one material, and then you're trying to figure out what that material is. Well, then you would use these other techniques. But if you have some unknown compound, from your sample, you don't even know where you got it from, and it may have more than one thing in it, that's when you tend to use this absorption spectrometry. Okay, so on all this, let's talk about what makes up a spectrometer, that term spectrometer. What's in that black box or white box, right? Well, generally there's, and it's not always the same, but generally there's several components that you need. You need a source of radiation, right? A source of the light, electromagnetic radiation. And then you have to have a monochromator, and it turns out the monochromator can be in front of your sample or after your sample. It doesn't really matter. You can send all the white light through the sample and then afterwards put the monochromator there, or you can put it at the beginning. But you have to have a monochromator, and what that monochromator does, it takes, if you have white light, which is light of many wavelengths, it just cuts out one of those wavelengths. Right? So now you only have one wavelength coming out, and you can vary it. Electronically, you can tell it to go to a different wavelength. You send that through your sample, right? Your sample's in some sort of container. And then after it comes through, you have a new intensity, and you want to, what you're interested in, how much is that intensity that came through it versus how much you started with, right? And you need a detector of some sort to detect that kind of radiation. So we need all those different things. Now, there are other kinds of spectroscopy that are, this is for absorption. There's also emission spectrometers, which is different, right? You're looking at the emission. And there's fluorescence spectroscopies, which we'll talk about. Okay. But this is just one type, right? And we'll broaden ourselves into the other types later. This is an absorption spectrum that you're measuring. Okay, so how does, we want to remind ourselves, how does electromagnetic radiation interact with matter, right? How does it interact? And the key there is that you can absorb light only going from one electronics or one state that you happen to be in. This is for atomic. If you're in a state, there has to be a state where you send, this is a lower energy state down here, and up here is some higher energy state. You have to come up with a photon whose energy is the same as the energy difference between the lower energy state and the higher energy state. If your photon has an energy that's not equal to this, especially in atomic, the material will just not absorb. It won't absorb. You need a place to land. All right. After you absorb that light, you have to end up in some state. So there's got to be a state there. So we're talking about the energy, right? And that energy, of course, is related to the wavelength or the frequency. In this case, it's easier to write it as the frequency. Remember, E is equal, or in this case, the change in energy, which is the energy of the photon that you're absorbing. An individual photon is equal to h, which is Planck's constant, right? That's just a number you look up, times the frequency, which is in hertz, right? So you take that frequency in hertz and you multiply it by Planck's constant, you get the energy in joules. And this is the energy for, this should be, this should be times 10 to the minus 34. It's a very small number. This is the energy of one photon, right? Not a whole bunch of photons, just one photon. And the number you can see, 10 to the minus 34 or something on that order, is very small for an individual photon. Okay, so that's what's required to absorb. You have to have a state where you land. But the other thing that can happen if you're in an excited state, right? The system can just spontaneously emit a photon and go back down to a lower energy state. And now the same thing, the energy of that photon is going to be the energy difference between two states. So it's very characteristic of where those states are, right? It really depends on where those states are. And as you remember, and maybe you remember, and for, say, atomic species, there's a fingerprint. Each atom has a different set of states, right? Different states, at least for atomic structures. Okay, so we're gonna collect a spectrum then, right? It's going to show, say, some emission at certain wavelengths or something. But what is the scale that we're going to plot here? What are the units of this scale that we have? Because a spectrum is usually some intensity, absorption, emission, or something, right? As a function of something else to be a spectrum. Well, here are the different kinds of units that you can see. The first are wavelength units, right? So that's the wavelength of the light. If you're dealing in the X-ray, that tends to be in the nanometer range. And chemists are fond of using this older term, which is angstroms, A-N-G-S-T-R-O-M, angstroms, and they have this symbol, which you have to look for very carefully on your computer to, if you want to use it. It has a little circle on the top, an A with a little circle on the top, capital A. And an angstrom is at 1/10 of a nanometer. So remember, the nanometer is 10 to the minus 9 meters. So an angstrom is 10 to the minus 10 meters. And chemists like to use angstroms in addition to nanometers. Physicists never use angstroms, so they like to use the nanometers. Okay, now when you get up to a different energy range, say in the UV visible region, then it's just mostly nanometers. You still see angstroms occasionally, because remember, the visible is from about 400 to 700 nanometers, which would make it 4,000 to 7,000 angstroms. All right, that's the range of the visible, and then the UV goes a little further out to shorter wavelengths. In the infrared now, you're starting to talk, especially the longer wavelength infrared. The shorter wavelength infrared is anything beyond 700 nanometers. They would call that the near infrared. But when people talk about infrared, they're usually talking about further out, and then we start to use micrometers, microns or micrometers, 10 to the minus 6 meters. You can also do a spectrum. You can convert any spectrum into energy units, right? You can convert a wavelength of the light to the energy of a photon, of an individual photon, and that would come out in the units of joules, or some very small fraction of a joule. And that's the unit that tends to be used by physicists. You don't see it too much in chemistry to plot it in terms of joules. And again, we talked about how wavelength can be turned into frequency, so you could plot it in terms of frequency. And frequency is always per second, and there's another name for that, which is hertz. So hertz and per second are the same thing. Now, chemists have another unit they like to use in the infrared, all right, and that is the wave number. They call it wave number, and that is the wavelength. It's 1 over the wavelength in the units of centimeters. So it has the units of centimeters to the minus 1. So if you see centimeters to the minus 1, chemists would call that wave numbers. All right, and so because it's proportional, it's equal to 1 over the wavelength, it's proportional to the energy. So lower number of wave numbers is lower energy, and higher number of wave numbers is higher energy. Okay, well, I'll show you some infrared spectra later. And finally, when you're working with the nuclear magnetic resonance, which is out in this radio wave band, they don't use any of these units at all, wavelength. They end up using parts per million, ppm. And I'll describe later why they use ppm. They don't actually talk in terms of wavelength or in nanometers. It's ppm because it depends on the instrument that you're using. So exactly what wavelength it is. The stronger the magnet, that changes the wavelength or the energy. And so instead they just talk about the shift in terms of parts per million shift from 0. So anyway, I'll show you that later. Okay, so now let's take a look at some atomic spectra, which spectra, of course, is the plural of spectrum, and then one spectrum, 2 spectra. All right, so this is an absorption spectrum here. This is just intensity. It's not normalized. So your light source, in this case, say, had some of this general shape here. It had a little more light in the middle here than it did at the side. So this part of it's coming just from the light source. But what we really care about are these absorption bands, right? These absorption bands, which in this particular case, which is, I guess, neon gas, they all look like they're about the same size. But they don't have to be the same size. Sometimes, for some atomic species, they're very deep, and other ones are very shallow, right? But what we care about in particular, I mean, that's important, but is exactly what wavelength these things are at, right? So that the wavelength for neon gas has these characteristic wavelengths, which in this case is in the visible, right? So this is the absorption spectrum. Now, if you take some of this neon gas, instead of having a bulb of gas and shining light through it, this was shining white light through it, and then looking at which wavelengths are absorbed. Instead, you take the neon gas and you say put it into a plasma, like a neon light. These are the things that they used to put in front of stores to light things up, or these light tubes. They put neon gas in there, and then you put a voltage across it, and the thing would break down, and you would take a lot of the neon and turn it into ionized neon, and then electrons would come back, and the whole thing's got a lot of energy floating around. But what you end up seeing is you end up with the energies coming back at the same wavelength. So these are exactly the same wavelengths, but they now occur as emission spectrum. It's coming from the gas. You don't need a light source to light this up. All you need is, in this case, a voltage source to cause the plasma to break down the neon gas. And then you just look at the wavelengths coming out, right? And this has some advantages. It can be more sensitive because you don't have this background. You're not looking at this background of this. You're just looking, because in between these, there's nothing, right? There's no emission coming at any other wavelength other than where these atomic transitions occur, right? Okay, so this is an emission spectrum and a absorption spectrum. This is also would be called a transmission spectrum, right? Because you're looking at the transmission, although hasn't been normalized. You're looking at the transmission, and you get less transmission. When you're looking at the absorption spectrum, this is the absorption. It's also the transmission spectrum. You're looking at a decrease in transmission, which is the same as the absorption. Whereas this is coming from an emission spectrum. Okay, and for instance, if you looked at this absorption spectrum, you could use this, the depth of this, to give you an idea of how much gas you had in there. If you've got more gas, this peak, or this dip here, is going to be deeper, right? And it's going to follow Beer's law, depending on what the concentration is in there for that particular species, what the concentration is, and also depending on the path length, whether or not you're going through just a millimeter of gas or a centimeter of gas. The longer the path length, the more absorption you're going to get. And that's all built into Beer's law. Okay, so these are all atomic spectra. These are discrete lines that you see in atomic spectra. But what about molecular spectra? What happens in molecular spectra? In molecular spectra, you don't get individual peaks as much as they get broad. They're not discrete peaks. They become broad. This is, I guess, chlorophyll B and chlorophyll A. I really don't know what the difference is. This is what makes plants green, apparently. But you can see these lines are very broad in comparison. In the earlier images, the widths of those lines were usually limited by the spectrometer itself, right? How good the spectrometer is. Otherwise, they become very, very narrow. Whereas these are not due to the instrument. These are due to the fact that not only do you have electronic transitions here in the visible region of the spectrum, but you've also got these rotational and vibrational states. So let's look, say, an example here. You're starting here at the ground state, right? You're starting here, most likely that your system is, you need energy to go to an excited state, and it usually comes back on its own. So your sample, when it's not too hot, is sitting at the ground state. So you can absorb up to this, say, excited state here. This is an electronic state, S2. You started with the ground state, S0, and you're going up to this electronic state. But in that electronic state, you have a whole host of different vibrational states. So these are the numbers of the vibrational states. And there's a whole bunch of them, right? And so as a result, each one of these lines becomes smeared out, right? It's smeared out. And the same thing happens when you emit light. You can emit light from any one of these states when you do an emission spectrum, and it's going to come back down to some ground state. It could come all the way back down to this ground state down here. But there'll be a whole series of them, and that gives you, again, a broad peak. So molecular species are characterized by broad electronic absorptions and emissions, right? So these lines end up being broad. Okay. But there's more that can happen than just this. You can also have what we call fluorescence, where the light that's emitted isn't the same as the light absorbed. And what happens here, this is not an atomic species. This is usually in a molecular species. You're starting here at the ground state, all right? We're starting down here, and you excite it up to this excited state up here. But then you can have that energy, this molecule now is up at this excited state. It could drop down, and it will very quickly, down to a lower energy state, the bottom state in this electronic transition here. So all these different vibrational states, they can share energy, and so eventually it just comes down here without emitting any photons. Instead, the energy that comes from going down here is transmitted to other types of heat and things like that, right? And then when you drop from here down to lower state, that emits a photon. So this is the absorption of a photon, right? You absorb going from the ground state up to some place. You could end up at any one of these states. But then when you emit, you start at the bottom one here, and you go down to any one of these, right? And the result is that this is the absorption peak, the blue line here. You absorb at higher energies than you emit from. So if you look at this is the absorption spectrum and the emission spectrum of some molecule. And unlike atomic species, they aren't very narrow lines, and they tend to be, the absorption one is at shorter wavelengths, which is higher energy than the emission spectrum. So you can see there's a little overlap here, but in general, the absorption occurs with higher energy or shorter wavelengths than the emission occurs, right? And that's characteristic of fluorescent spectra. So you shine light in, and then light comes back out at generally a lower wavelength, right? A shorter wavelength. And it can be a lot shorter. These are showing them just overlapping, but it comes out a lot shorter. So you can, for instance, looking for a sample of some large organic, you can shine light here at this wavelength, right? And then look for light coming out here. So you're shining light at one wavelength and looking for the emission of light at a different wavelength, but it's always at a longer wavelength, right? Because you can't get more energy coming out than you put in. All right, so this is called fluorescence, where it trickles down to a lower energy state and then emits, all right? And there's some lifetime involved with this. It doesn't happen as quickly, but it happens relatively quickly. But there's another kind of way that light is absorbed and then re-emitted at a different wavelength, which is much slower. All right, so fluorescence is kind of fast. The other one is called phosphorescence, and these terms are very confusing. They're both considered luminescence because you put light in and it came back out somewhere else. But fluorescence is relatively fast compared to phosphorescence, which can be relatively long. This can be, a second or seconds later that the light comes out, as opposed to very short times. And let me try to describe what's happening here. So again, let's see, here's the absorption. This line here is the absorption, all right? You're absorbing to somewhere in this state up here, all right? You're going from this ground state here, which is this black one is the ground state down here. That's where you start off with, and everything's nice and cold, right? But you put some energy in, and you send it somewhere up, say up here in this higher excited vibrational state of this S1. S stands for singlet, right? Now, once you're in this state, right, because you absorbed into that state, again, we said the light can come back down here very quickly, or the energy can be removed very quickly without emitting light until you get down to the ground state here of this excited state, or the lowest vibrational state of this excited band, all right? But now, once you're there, the light can then pass over from this over to S0 here, right, which is back a very excited state of the ground state, and the light can completely disappear or the energy can completely dissipate without emitting light. Right? So this doesn't have to have any light involved. All right? Now you can have fluorescence. Here's fluorescence coming down from this energy level down to the ground state. And here they give you some times, 10 to the minus 8 to 10 to the minus 4. So microseconds or less, right, in the microsecond range or less. And that's happening, that's fluorescence. But the other thing that can happen is you can go from a singlet state to what's called a triplet state. Now, you can't easily absorb light from a singlet to a triplet. So you don't see light going from the ground state here up to a triplet. Just the way that the spectroscopy works, light doesn't get absorbed, go directly to a triplet very easily. So most of the time you ended up sending it into a singlet state. But you can do what they call intersystem crossing. The system can go from this singlet state to a triplet state of the same energy, or roughly the same energy. And then again, you lose energy going down to the ground state of this triplet. So you've gone up here, you've come down in the singlet, intersystem crossing, and now you lost energy and you're at the bottom energy here of this triplet state. You're at the bottom energy of this triplet state. And now you're kind of stuck there because, again, the light doesn't want to go from a triplet state back down to this is a singlet state down here. Down at the bottom is a singlet state. So it just sits there. It sits there and it's relatively stable. Right? Now, if you bump into another molecule or something happens, you might actually just send the energy back over to a singlet state and then lose the energy, and again, without any emission of a photon. You just transfer the energy without emitting a photon. But occasionally, a photon will get emitted through this not very well allowed transition. But it took so long that the lifetimes now, this is now in the, this is like 100 microseconds up into the 100 seconds range. So it can be a long time, a long time. I guess an example of this is, if you remember, sometimes your old watches, or maybe you had these things as a kid, they were up in your, on your ceiling, and when the lights are on, they get energy, and then they turn the lights off and you see stars on your ceiling, or you can see on your wristwatch, you can see the hands of the wristwatch and the numbers, because even though they were lit up a long time ago, this is many seconds, all right? So it can hold that energy for a while. So that's phosphorescence. Phosphorescence takes a lot longer, all right? Okay, what else can we say about this? Fluorescence can be very sensitive, right? Making a measurement like this. And the reason is the way the spectrometer works. We were talking before about absorption, for instance. And absorption, you're sending in a lot of light, and then you're looking for a small decrease in that amount of light, which that's difficult to measure. You're sending in whatever it is, so many photons per second or so many watts of light in, and you're looking for a small decrease. Well, it's hard to measure small changes in a big number like that. But instead, if you send light in that's, say, in the blue, or in the ultraviolet, tends to be in the ultraviolet, so you shine light in the ultraviolet, and then you look over here in the red, all right? Well, there was no light in the red, so you're not looking for a small difference. You're looking for red where there wasn't any light. So now you can have a very sensitive detector. So fluorescence tends to be much more sensitive than just absorption, if you can set it up right. It can be at the parts per trillion level, so you can have very little material there. And this is used a lot, for instance, when you're looking around for fingerprints in forensics, when they shine a UV light, one of those black lights. This is firstly done with your naked eye. You can put a UV light onto it, which your eye doesn't pick up any UV, right? But then if it starts to fluoresce in the visible, you can see it with your naked eye. And they use this to look for fingerprints. They look for blood, things like that, any of these bodily fluids that might be there, because those kinds of things fluoresce, whereas the piece of wood or glass or whatever metal that it's on doesn't fluoresce. Okay. Now we're going to switch into different types, to talk about different specific types of spectroscopies. All right, we're going to focus more on different spectroscopies.